Thank you. My name is Jernej. This is a joint work with Damian Kužnar and Professor Matjaž Gams. I work at the Department of Intelligent Systems here at Jernej Zupancic Institute. I will talk about model selection on the JSI grid. And the goal of the experiment was to test the newly available JSI grid on a common use case, which is a model selection. So a model selection use case. So this is the outline of the talk. I will quickly introduce the JSI grid. I will talk a little bit about the model selection, about the experimental setup, quickly go over the results, and talk about my experience at using the grid at the Jernej Zupancic Institute. So the JSI grid is part of the Slovenian initiative for national grid. There are also other grids available in this SLING association. For instance, the Arnes grid or the grid at the University at Nova Gorica. The JSI grid is available to every researcher at JSI. You only have to apply to the virtual organization and you will get the access. The grid has nearly 2,000 CPUs available. There are also some machines with the GPUs, but I'm not sure what is the state of those machines, if they are usable yet. The grid uses the advanced resource connector middleware. This is a set of tools to submit and gather the results from the grid. It's developed by the European Middleware Initiative. It's been in development since 2002. And the grid uses a batch system. That means you specify a job, a task, and you submit it to the grid. The grid then does the computation and spits out the results, which you can then gather for further analysis. So, model selection. Model selection is basically an optimization problem where you try to find the algorithm A that has some parameters lambda that, given some finite set of x's instances, models the relation in the attributes of x, and then what we try to do is you try to minimize the expected loss over the instances coming from some ground truth distribution. So I promise this is the last formula. So a model selection is a hard problem. Why? Because you try to do a minimization over infinite infinite sequence of x's, which you don't have the access to, at least usually. You only have a finite set of instances, D, and you would like your algorithm to generalize well also to the unknown, previously unseen x's. It's also a hard problem because there are no gradients available, so you cannot use some standard numerical optimization procedures to optimize it. And the search space is very complicated. It's hierarchical, so first you can choose from among a large number of algorithms. Each algorithm has its own parameters, and those parameters can be either categorical or ordinal or numerical. And the search space usually is pretty large. So it is a hard problem. There are many model selection algorithms you could choose from. So the first, going from the, let's say, least intelligent to a little more intelligent. So the manual search, where a researcher tries to build an intuition about what algorithms to use and what parameters to use for a specific problem. And then he guides his algorithm and parameter choosing based on this intuition. Then there's a grid search, where this researcher discretizes the search space and then just tries all the combinations, which is quite time consuming. So then there's the random search. In random search, you specify a distribution over the algorithms and the parameters of the algorithms, and then you sample from this distribution in order to evaluate the models. And this is usually much better and faster than the grid search. Then there are evolutionary algorithms. They're very good because they do not require gradients. They can work in complicated search spaces, so they are an option. And then the more novel algorithms are sequential model-based optimization algorithms that try to model the relationship between the algorithms and their parameters and the performance of the algorithms and their parameters. And why sequential? Because at each step they gather the information from previous evaluations, and then they propose a new solution to be evaluated, which is usually a trade-off between the improving the model that you are building and getting the best model. So we have used in our experiment, we have used the random search. Why? Because it's very easy to implement. It is very robust. It doesn't require any communication between the computing nodes, which was a big bonus for the implementation on the JSI grid. So the random search, so the setup, we have used the Miniconda package manager to set up our environment in Python. So when you submit a job to the grid, first the environment is set up, and you can only modify so you don't get the root access, you only have the access at a user level. And this Miniconda environment can do that. It sets up an environment with all your specified packages and libraries. And then the algorithm is run. And this algorithm, as I said before, it samples from the available algorithms and their parameter spaces. We have used scikit-learn and XGBoost for the modeling task. Then the model was evaluated. Because it was a binary classification task, we used the area under the curve score, and we used the five-fold cross-validation predictions to compute the area under the curve score. Then the performance of the model was reported to the central node. So I said before, no communication between the computing nodes is necessary, but in order to gather all the results, we have reported in real time the results of the evaluation to a MongoDB database. And then all the steps are repeated until either our time limit expands or the job crashes. So, quickly about the METIS data. METIS data was gathered during the METIS project. It was a project whose goal was to predict student performance at the end of the grading period. The data included about 70,000 unique students at 4 subjects, you see there, a little below 2 million instances, where each instance was of the form Student with ID 1 in October 2016 at subject mathematics has these and these grades, so at the end of the month. So this was one instance. We have engineered 32 features. They were derived from the grades, absences, missing the exam, so if the student was missing at the exam or not. So simple descriptive statistics from those attributes. Quickly about the results, which are not the main point, but still. So the gradient boosting classifier performed best, but not far behind was the logistic regression with the right parameters. And this was actually the one we have chosen to implement in production, because the logistic regression is much more explainable than the gradient boosting classifier. So here all the evaluated models. As you can see, the performance is remains pretty much the same all the way up to here. There were only one evaluation for the naive bias, because naive bias in the scikit-learn does not have parameters, so one evaluation is enough. And there was one evaluation of the support vector classifier. Why? Because only one evaluation successfully finished, all the other ones crashed. So only one was obtained. So the grid experience. Frequently, at least that was the case a few months ago, you would get some strange errors which were not the fault of the researcher submitting the job. And that is why the random search was chosen, because the communication between, there was no communication between the nodes necessary, and if one job crashed, it means no problem for other jobs. Okay. There was also no connection between nodes in a grid available, and still is not, but the connection between nodes is in process of establishing, from what I've been in contact with the administrators. The grid only allows batch jobs, which is fine if you have one thing that only needs to be computed. But usually at machine learning or data science or whatever, you would like to first get the information about the performance of the models quickly. And for this you would need some interactive work, which is currently not possible on the grid. So only batch jobs are possible. So these are the recommendations or best practices. It's best to parallelize your code so that each worker or a node, computational node, can work on independent task. Why? Because if an error occurs in your job, which you could potentially handle with software, but because it's not always in your, let's say, capabilities to catch all the errors, they could be a system error or something like that. If this job gets an error, then only this job will be cancelled. So it would not affect other tasks if you can parallelize this way. We also propose to use some local database for gathering the results in real time, because when a job crashes, there's a probability that you cannot gather the results. For instance, if you save the results in a file during the job run, and then the job crashes, there is a chance that you will not get the file back. Also, local testing environment is useful, because when you submit a job, it takes a couple of minutes for your job to be processed by the system and then accepted or not, and then the environment to be set up and the job to be run, and then the results to be gathered. So a long time, and there is a high chance that something will go wrong. So if you can prevent this, use some local testing environment. In our case, we've used the Docker containers to spin up a grid-like environment where all the code was loaded and the packages were installed. So we tested before running on the grid. And another useful thing is to have some scripts for submitting the jobs and obtaining the logs, because if you parallelize your code, you will need to submit multiple jobs, and scripting can automate this and speed up the process. So in future work, we could, so we've tested the random search. We could test or implement some smarter parallel optimization algorithms to use on the grid. And to leverage the full power of the grid, we would need some kind of connection, which will become available soon. We could advance the model selection with automatic pipeline building, so not only the algorithm and the parameters, but also pre-processing steps, combining multiple models and stuff. And we would like to maybe develop a tool that would automate all of this. So to conclude, so model selection is a computationally intensive task, and it makes sense to use the grid since it's available here at JSI. Random search was very easy to implement. It's robust and it's completely viable model selection algorithm, and it is also quite hard to beat. Okay, so JSI grid can easily be exploited for those computationally intensive tasks, and I encourage you to use it. And also the model selection. So in our case, we have not chosen the best performing model. We have chosen the best explainable model, which was also quite okay performing. So you have to make a trade-off. And all the codes and scripts are available online. So thank you.